This is a video on the binomial distribution and hypothesis testing. So I'll be going over 1 and 2 tail tests. And I wanted to do this because I was in class yesterday, I think. Yeah, yesterday. And we were doing hypothesis testing. We were only doing 1 tail tests, but I noticed that quite a few people were confused about it. And I knew that this wasn't just specific to my class, because if you've seen my AS paper walkthroughs, you'll have seen that I've done hypothesis testing before, and when I was learning it for the first time as well, I was quite confused with it as well. I mean, I was even my voice, I might have even been a bit like, might have just explained it a bit badly during those videos, even just because I didn't understand it fully. And so, because I know now that this isn't just a particular problem experienced by just a few people. I feel like it's something that a lot of people struggle with. And even in my other maths class, one of my teachers said that he doesn't actually think that anybody, any student at all, actually understands what hypothesis testing is and why it works. And so I've made this video to try and explain it as best as I can to help you to understand it. I've spent quite a few hours putting all of this together and trying to explain it as best as I can to help you understand. And it will be a long video, so I'll try and put the timestamps in the comments maybe for the 1 and 2 tail tests. But I do really think that this video will be valuable, so please watch it if this is something that you struggle with. So a binomial distribution is just a curve which shows the probabilities of certain events. Okay, it looks something like this. Okay, it's a binomial distribution and it will touch the x-axis eventually. Okay, now on the y-axis, you don't really see the y-axis drawn often, but on the y-axis you have the probability of the event, and then on the x-axis you have the number of successes. Okay, so for example, landing heads when flipping a coin 100 times, right? If you flip a coin 100 times and there's a 50% chance of getting heads, you expect to get 50 heads altogether. So the probability of getting 50 heads is just 50%. So here would be 50, and then a success, i.e. a head, so getting a head 50 times would be here, right? You'd expect that to be the peak of the curve, right? Because that's the highest probability. There's nothing that you could get 100% of the time, unless it was a biased coin, which it's not. So 50 heads, probability 0.5. Okay, say if you got 40 heads, you might have a probability somewhere here. So it's a bit lower than 50%. I don't know what it is exactly, but because I'm just not thinking about it right now. But it would be lower, right, to get 40 heads, because it would suggest that the coin might be biased against heads. So there's actually a less probability of getting heads. It could be higher. So if you got 60 heads, it could be somewhere over here. But the reason why I'm doing this is to show that on the right hand side and on the left hand side, it is both less than the peak. So this has a probability of, say, like X%, and this one also X%. Now in this specific example, this probability is the same as this one. They're on the same horizontal line, but that's just because this is symmetrical. Now usually you won't see a symmetrical curve like this. It's just not very likely. But if it was, then say 40 would be the same probability of getting 60. So the same 10 width of 10 either way. Okay, this curve is called a bell curve. Okay, and that's that. Now they have a bunch of different shapes, so it can look like this, it can be more stretched out like this. So that's just to show you that there's quite a few things that it can look like. Now the probability of an event is given by this formula, which you might have seen before, and I'm guessing that you have seen it because if you're doing binomial distribution, you will have likely been shown this formula, so I won't go over it too long. But say we flip a non-biased coin 10 times, what's the probability of getting a heads 3 times? Okay, so n here is the sample size, and r is just how many we're choosing to be successes. P is the probability of getting a success, i.e. of getting a heads, and then 1 minus p is the probability of not getting a heads. Okay, and I'll explain the powers in just a second. So there's 10 samples. Okay, we're choosing 3 of them to be heads. Now the probability of getting heads is 0.5 because it's non-biased, and the formula is telling us that this 3 should be there as well, okay? And then 1 minus p, so 1 minus 0.5 is 0.5, and that should be 10 minus 3, so 7. Right, what this part here is actually saying is, first of all, we're going to get 3 heads in a row, so 0.5 times 0.5 times 0.5, hence 0.5 cubed. And then we're going to get 7 tails in a row, so 0.5 times 0.5 times 0.5, etc., until you get 7 tails. Okay, and that's the probability of this event. Now, what this function on the left here is doing, this is called the choose function, or the binomial coefficient. What this is saying is, well, I'm going to times this number by some other number here. Okay, and that number just represents the number of ways which you can order this. So, for example, you didn't have to necessarily do this. You could have gotten 7 tails and then 3 heads. You could have gotten 2 heads and then 7 tails and then 1 head. You could have gotten 1 head, 1 tail, 1 head, 6 tails, and then 1 head. You know, these are all possible combinations of still getting 3 heads. Okay, so all of these possible combinations, etc., we're going to multiply that by the probability of getting 1, and then that way we'll have all the total probabilities. So irregardless of whether we get, say, 3 tails and then 3 heads and then 4 tails, or any of these and more, we're still going to find the true value for the probability of getting 3 heads, irregardless of what order we get that. Okay, so this is the probability of getting 3 heads and then 7 tails, because if we're flipping it 10 times and we get heads 3 times, we must get tails the other 7 times, and then this just tells us how many different combinations there are to do that. And if you put that into your calculator, you'll get this number here. Okay, now let's just go over notation. What this is saying is that x is given by the binomial distribution, and then this. Okay, that's a given, but it's fine. You can also read it as x is distributed binomially as this. Okay, where n is the sample size and p is just the probability. X is what you want to get. So in our other example, we said x is just the number of heads. X here, x is just called the specific term. The term that we use for it is the test statistic. So that's what you want to get. So going back to the other example, x is getting a heads. Okay, so we could say that x is distributed binomially, i.e. getting a heads is distributed binomially. That should have a b there. With a sample size of 10, probability of 0.5, and we're looking for the probability that x equals 3, and that would equal the same number that we got last time. Okay, there should be a b there. The b here just means binomially. You might see an n sometimes for normal, and if you do further maths, you'll look at the Poisson distribution. Hypothesis testing now. It's carrying out a test to determine the likelihood of a probability or claim being true. Okay, let's look at an example. Say I buy a product from a company, and they tell me that there's only a 1% chance of the product being faulty. Right. Say I buy 100 products and 20 of them are faulty. It's quite likely that the company's estimate is going to be wrong, because if only 1% were going to be faulty, I would have only expected to get 1 product that was faulty, and then I would have said, yep, their estimate's pretty fine because that's what I got. But if I'm getting 20 times more of that, I'm going to think, well, actually no, I think that this probability should be higher. So I think they're wrong and I'm right in this case, given this sample. Okay, what if instead I buy 100 products and 3 of them were faulty? Is it likely that the company's estimate is wrong now? Well, here it's much more difficult to determine than here, because here there was a massive difference between 1 product being faulty and 20. Now here, the difference between 1 being faulty and 3 being faulty isn't as significant. Notice the terminology, significant. So how can I say, is it still significant enough? Is that difference of 2 significant? I'm not sure, but we do a hypothesis test to determine whether that is significant or not, because if it is significant, then their estimate was wrong, and so I think that the probability should be higher because I got more that were faulty. Okay, the significance level is just a threshold that we use to say if our probability is significant or not. Now, if that doesn't make sense to you right now, just leave it. When we actually get into doing questions, you'll understand it. Okay, like I said, this same example here. Okay, I may say if 4 or more products are faulty, then the company's estimate is wrong. Okay, so my significance level is just a threshold. So I'm saying if 4 or more products are faulty, then the company's estimate is wrong. Okay, well, this is less than 4, so I can say, you know what, their estimate is fair enough, right? It's not too big of a difference. So I'm just going to say their estimate is probably not wrong. Okay, if I get, say, more than 4, say I get 5, I'm going to think to myself, wait a minute, actually, maybe their probability is a little bit off. Maybe it needs to be just a tiny bit higher. And so in this example, this would be my significance level. It would be this statement here. Now, in practice, significant levels are not given like this, but this is just oversimplification, and we'll get to how they're actually used later on. Okay, now a significance level is given as a percentage, okay, and it represents a percentage of the area under the distribution curve. So remember at the beginning when we saw the bell curve, the significance level is just some area under it, okay, and we use the letter alpha to represent the significance level, and this will be given in the question. Okay, for the AQA spec, this will be given in the question. In edXL, you can be asked to find the significance level, but I'm not going to be going over that. So say we have a bell curve that looks like this, and let's say the significance level is 5%, right? So alpha is 0.05. If we're looking at one tail, right, it doesn't matter whether we look at this one or this one. It depends on the type of question, and I'll get to that later on, like I said. So say we pick here. Okay, for the record, the curve is not usually symmetrical. I've just put that as a note there. But we're saying if we just draw a line here, the significance level being 5% just means that this area here is 5%. Okay, it could have been a really small slither here, right? But the thing is, we always take significance levels from either side. So 5% going from the right or 5% going from the left. Okay, and whichever way you're coming from depends on what the question's actually asking. Okay, so this here is 5% of the area. Okay, which means that this here must be 95% of the area under the curve. This does actually go down and touch the x-axis, but it's just goofy. Okay, we might have it be on this side, so this would be the 5% of the area, so that would be the significance level here, and then this would be 95% of the area. Okay, I'm going to go into a question. I know this seems a bit fast and like I've just jumped into it straight away. I'll try and go slowly, and trust me, after doing a few, you'll get used to it. Okay, now let's have a look at just a tiny bit more notation. There's this thing called H naught, okay, or HO. This is called the null hypothesis, and it's just the default claim, right? It's just what we're assuming to be true at the beginning, and this is what we're testing to see if it's true or false. Okay, so for example, in this question here, Martin's growing cucumbers from seeds, and he found that 70% of all seeds successfully germinate and grow into cucumber plants. So we're saying that the default claim, right, is that the probability equals 0.7, 70%. Okay, he decides to try a new brand of seed. Okay, and the producer of this brand claims that these seeds are more likely to successfully germinate. So the alternative hypothesis is you can think of it as the other claim, right? This is what we think might be true, but we're not fully sure. This is what we're assuming to be true now, for now. Okay, the alternative hypothesis is written as H subscript 1, and that probability is going to be greater than 0.7, because we're told that this guy thinks that the probability is going to be greater than 0.7. Okay, so this is what we default believe to be true, and then this is what we think might be true. Okay, now Martin sows 20%, 20 of this new brand of seed, and 18 successfully germinate, which seems quite high. Okay, carry out a hypothesis test at the 5% level of significance to investigate the producer's claim. Up here is just a reference to the paper if you want to have a look at the question. Now, 5% level of significance, okay, so alpha, the significance level, is 0.05 or 5%. Okay, remember, we always need to define x. If you don't define what x is, i.e. the test statistic, which we went over earlier, you'll drop a mark. X here is the number of seeds that germinate. Okay, that's what we want. We want to find out the number of seeds that germinate. Okay, so here x is just a number of seeds that germinate, because that's the probability. That's what the probability is relating to. Now, in a hypothesis test, we always do this step here. We're assuming H naught to be true. Okay, and I'll explain why. So say somebody's making a claim saying, no, I think that this H naught is actually false. Okay, and we'll say, okay, well, let's look at what H naught is actually doing. If H naught seems unusual by looking at its behavior, then we can say, you know what, H naught is probably not true. So let's assume H naught to be true, and let's just see how this plays out. Okay, let's see what happens. Okay, next we set up what the distribution looks like. So we're saying that X is distributed binomially with a sample size of 20, because the sample size is 20. Okay, and then the probability, remember, NP, probability being 0.7. That's because we assumed H naught to be true. Okay, now Martin, he said 20, and he's saying that 18 successfully germinated. So if this person's claim is true, then we're expecting this to be greater than 18. Right, so we're saying, what's the probability that X, i.e. the number of seeds, is greater than or equal to 18? Okay, hopefully that makes sense. So Martin's saying that the probability should be greater than 0.7, and so we'll say, okay, what's the probability that it is greater than or equal to 18 then, right? So if this is greater than sign, this will always be greater than or equal to. Your calculator will by default be on the less than or equal to sign when you're doing binomial distributions. So you have to change this slightly. Okay, I'll show you how you can change it. So we know that this probability is just the probability that X is either 18 or 19 or 20. Okay, which is 1 minus the probability that is 17 or 16 or 15 or 14 or 13 or 12, all the way down to 0. Okay, hopefully that makes sense, because your calculator only accepts it in this form, where it's in the less than or equal to. So you have to manipulate this. It's like saying, okay, imagine we only want 18, 19, or 20. Well, what if we get 17, 16, 15 all the way down? So everything less than or equal to 17, but then we do 1 minus that, i.e. that will just get us this. Okay, so this is identical to this. We've not actually changed anything here in terms of value. Now, let me just show you how to put this into your calculator. Depending on the type of calculator that you have, it will be different. But I've got here, it's called the CG50, I think. I'm not too sure. I'll try and be as general as I can. So what you're going to want to do is press menu. Now, this screen might look a bit daunting. There's a few things. Your calculator might say statistics, or it might say distribution. If it says distribution, click on distribution. If it says statistics, click on statistics. Okay, not all calculators will have the ability to do binomial distributions, so just be wary of that. Okay, now if you're on the same calculator that I have, you have to press on distribution. If you're on a different one, then it'll say either list or one variable. Press on one variable. Okay, click on binomial if it's there. Now next on your calculator, you'll see either binomial CD or binomial PD. Now binomial PD just means that the probability that X is equal to some value, but we're not equal to some value. We're looking for a cumulative probability, i.e. we're looking for the probability of 17 plus 16 plus 15 plus 14, and then we're doing 1 minus that. Okay, all the way down to 0. So we want the cumulative one, so we'll press binomial CD. Okay, now here it might look different again. Your n will always be X is less than or equal to whatever n here. Okay, the number of trials, which will be your capital N. Sorry, ignore what I just said. Your capital N will just be a number of trials. So in this case, n is just going to be 20. So let's put that as 20. Okay, the probability is 0.7. Okay, ignore the lower bound. You can use it. You might want to search up how you can use that. But put in your X as 17. Okay, and so let's go down, let's click execute and see what we get. We get 0.965 to 3 decimal places. So let me just move that out of the way. And we're doing 1 minus that. And that will get us 0.035. Always go to 4 decimal places. I've not gone here just because it's just simpler to write out a bit less than 4 decimal places on PowerPoint. It doesn't actually matter for me right now because I'm not being examined, but do go to 4 decimal places. Okay, I've just removed a bit of this just so it looks a bit cleaner. Let's draw out the distribution, so the bell curve. Okay, might look something like this. Just do a rough sketch. Doesn't actually matter. Now, because we're looking for the probability that it's greater than, okay, if you're looking for the probability that it's greater than, then you're going to want to be on the right hand side. Okay, you're going to want to be on the far right. Okay, so that means that alpha being 0.05 or 5% is going to be here. Okay, and we're going to look at everything after it. Okay, I've just put a line here to say that everything above this is greater than 5%, and everything below this is less than 5%. Okay, this is 3.5%, this is 5%. Now, 18 or more is maybe somewhere here, because this probability is 3.5%. So that's 3.5%, and 18 or more, so 18, 19, and 20 is all of this area here. Okay, this here is 5%, that's our significance level, and this is everything here. Okay, so within our significance level, we're actually including this this probability here. Okay, now everything within this blue region is the reject region. So everything that's within it, we reject it. Okay, remember we assumed H0 to be true, but H0 is telling us that our test statistic is extremely unlikely. So it's telling us that this probability is extremely unlikely. Okay, well, it can't have been that unlikely if we got that result many times, right? So H0 must be false. Okay, we reject H0 because it's less than 3.5%, i.e. it's so extreme that H0 is saying that's so unlikely that it'll probably just won't happen. Okay, well, it did happen quite a few times, so it can't have been that unlikely. So we're saying that H0 is false, and our evidence for that is this sample here. Okay, another way that you can think about it, I think that this is the easier way to think about it, is this percentage here that you're calculating. Oh, by the way, I've just forgot to put that. If P here, if this probability equals exactly the significance level, so exactly on top of it, then just reject H0. Okay. Anyways, so this probability here, right? This is the probability that it was a coincidence. That's the way that you can think about it to really help you. So whatever probability you get here is that it's a coincidence. So we're saying that the probability of getting 18 or more, the 3.5, there's a 3.5% chance that we get that, but that's a probability that it was a coincidence. So the probability that it was a coincidence is really, really, really low, which means that there's a high probability that it was not a coincidence, i.e. there is a significant, this is significant, right? So, this is not a coincidence because the probability of it being a coincidence is so low. Thus, we reject H0 and we accept H1, the alternative hypothesis. Okay, I'll just say that one more time. The probability of this being a coincidence is 3.5%. That's a really low percentage, right? So it's likely that it was not a coincidence. Okay, 5%. Okay, this represents the probability that it can be a coincidence. So say if we get a 20% chance here, okay, 20% chance, to be honest, there's a 20% chance that it was a coincidence. 20% chance is, it's not too low. It's fair, I think. Okay, so if there's a 20% chance it was a coincidence, then we can assume H0 might just be true. It might just have been a coincidence. It might have just been, yeah, it might have just been a coincidence. If we get, say, 4%, right, so still lower than significance level, then we can say, well, now I'm starting to think that it wasn't just a coincidence. I'm starting to think that H0 is false, because this is such a low probability of it being a coincidence. So I have reason to believe that H0 is false. Okay, hopefully that makes sense. Let's look at another question. So here we're saying that 14% of the visitors to a website are under the age of 30. Okay, 14%, that's the base claim. So we'll just say that H0 equals 14%. Okay, Now, there was an advertising campaign to test whether the campaign was effective. They took 60 people and they found out that 15 of them were under the age of 30. Okay, we want to carry out a hypothesis test at the 5% level of significance to investigate whether the sample provides evidence that the proportion of visitors under 30 years of age has increased. So they're saying that the probability of people under the age of 30 has increased. Okay, well, if it's increased, that means the probability is increased. Okay, so they're saying that the probability they think is actually greater than 0.14. Okay, the total significance level was 5%, so A is 5%, alpha is 5%. Okay, the sample size is 60. Okay, and the probability, assuming H naught to be true, is 0.14. Okay, this is assuming H naught to be true, just to see how it plays out and see what goes on. Okay, remember we need to actually define this test statistic here. I forgot the B again. That's my bad. There should be a B here. I think you'll drop a mark if you don't do that, actually. But yeah, X is the number of people under 30 years old. That's what we're saying here. Okay, for the record, this, you have to say it out exactly like this. If you don't, you'll drop a mark, right? If you put like a dash or something, or if you just maybe don't put a colon, you can drop a mark. You do need to put H naught, colon, and then whatever the default probability is, then H subscript 1, colon, whatever you think the probability actually is, whether it's higher or lower or not equal to, as we'll see later. Okay, I think some people put an A here to show alternative hypothesis. Don't risk it, just put 1. Okay, we're looking to see that because we're saying we're looking to see has the probability increased, right? Only 15% of the people out of 60 actually visited the site. Okay, so we're saying, is that number higher? Is this significant? Okay, well, this number here is 15, 16, 17, 18, all the way up to 60. Okay, we're looking for X being all of these values up to 60. That's 1 minus the probability of all of them being less than or equal to 14. Okay, and I've put it in this form, like I said, because the calculator wants it in this form. Okay, so let's get out the calculator again. Let's see how it looks like. Okay, let's get rid of that. So statistics, okay, we want to go up. The upper is going to be 14. Yours might not say upper, it might just say X. That's fine. And the number of trials is 60. Okay, and the probability is 0.14. So we'll put in 0.14, and then we'll execute that and see what it says. We'll get 0.9835 or 0.984. Okay, so 1 minus 0.984, which is 0.016. Okay, so the probability of X being greater than or equal to 15 is 0.016, i.e. the probability that this was a coincidence, that this sample was a coincidence, is 1.6%. I'm looking at that and I'm thinking that's quite a low percentage of it being a coincidence. I'm starting to think that H naught is false. Okay, significance level, we're looking for greater than, so we want to be on the right side of the tail, right side of the bell curve. Okay, and this is 5%. The number of successes, remember, on the bottom is 15. Okay, and that equals 1.6%. Okay, and this is everything below, greater than it here. Okay, and then this is everything here. That's that full area. This is 1.6 of the area, 1.6%. Now we're saying that there's a 1.6% chance that this is a coincidence. Okay, well, H naught is saying that our test statistic, getting 15 or more people, is extremely unlikely. Okay, well, like I said, it can't have been that unlikely, because, you know, we got it. Okay, and because the probability of it being 1.6% as a coincidence is less than 5%, we reject H naught. Okay, we expect P to be more than 5% if H naught was true, i.e. the probability of it just being a coincidence might be 40%, 30%, 20%. You know, if the probability of it being a coincidence was fairly high, then we can say, you know what, H naught, there's actually no reason to reject it, because it could have just been a coincidence, because the probability of it being a coincidence was quite high. So we reject H naught because 1.6% is less than 5%. Okay, there's enough evidence to suggest that H naught is false. You need to say this last point here to get the last mark. Okay, let me just say that again. So let me just actually talk about the significance level just a bit more. Now, the significance level is saying It's a threshold, like I mentioned earlier, to help us determine whether H naught is true or false, right? It's the minimum number that if it was a coincidence, right, then we reject H, then we accept H naught. Sorry, no, reject H naught. Even I'm getting confused. Sorry about that. But yeah, so we're saying that if the probability of it being a coincidence is 5%, i.e., exactly this, then that's still quite a low percentage, right? We always do it relative to the significance level, just because it's just a cut-off point. We have to make at least one cut-off point somewhere, right? Because how do we say, well, 16% coincidence? That's actually quite fairly low, you could say maybe. Well, how do you know? Somebody might say, well, I think that's high. Somebody else might say that's low. So we just do a cut-off point at the significance level, which is 5% in this case. Okay, so if the probability of it being a coincidence is less than 5%, then that's quite low. If it's a bit higher than 5%, then we can say, you know what, that's fairly high. Just as according to this arbitrary line that we've cut that we've made, that the question has given us. Okay, let's look at imagine this didn't say increase, imagine it said decreased. So P for the alternative hypothesis would be less than, because we're looking for it to decrease. Okay, this is still the same here. We still assume H not to be true always. Now we're looking for the probability that X is less than or equal to 15, because this is a less than. Okay, and that is 0.99. If you put that into your calculator, I'm not going to put it into my calculator because I've shown it twice, and hopefully you know how to do that. This is 99% chance. This is a 99% chance, right? It's less than, all right? So we're going from the left forward, so this would be a 5% here for the significance level, okay? And the 99% chance is here, okay? This 99% chance, remember, from the left, so it's all of this. So what this is saying is that there's a 99% chance that this was a coincidence. Well, if I think to myself, if somebody's trying to make a claim against me, but I know that there was a 99% chance of that specific claim being a coincidence, then I'm thinking, well, it's not really good evidence, is it? Because there's a really high chance that it was just a coincidence. Okay, and so we actually accept H naught in this case, because we'll say, well, because this is actually greater than the significance level, there's a high chance that it was a coincidence. So we just accept H naught. The actual correct terminology would be, you would say, we fail to reject H naught. I don't know why, but that's just what you say, I guess. It doesn't matter, you won't drop marks for saying that in a test. Now, if you still don't understand that, and you're just the type of person that maybe isn't too big of a fan of maths, well, you will have been because you picked it for A-level maths, or further maths even. If for you maths is just something that helps you to do what you want to do later on in life, and you're not actually super interested in it, and you just want to get a good grade to help you get on to do maybe a law degree or a degree in I don't know, medicine or something like that, and you just want to pass maths, and you're not too bothered about the intuition, you just want to do well and not think about it anymore, then I hope I'm not being mean. I hope I'm not being mean by saying that. But I do understand that a lot of people out there, because I tutor two girls, um, both in year 10 actually, and I think to myself, there's so many things that I would like to teach them, and there's so many things that would be nice for them to know in maths, right? But it's not actually necessary. I mean, I'd like for them to know, and they might find it interesting, but it's not what they're passionate about. It's not what they actually want to do in the future. And so they just want to pass. So I always try and explain it in the easiest way, which should be done anyways, but I'll miss over some things which I might think, well, that's not really relevant to them, even though it's a cool extra thing that you might like to know. For example, what the significance level actually means, or interpreting it as a coincidence and stuff like that. I think, well, maybe it might just be easier to teach them something like a rhyme, just something really easy to remember, and you know, they can answer 99.999% of, even 100% of questions actually, just with this. Okay. And so if you're watching this video and you're that person, okay, and you're not actually too bothered about the intuition, and you don't want to think about coincidences and stuff like that, then just remember this one thing here. If the percentage is low, reject HO. Now, I saw this in a comment section somewhere, and I thought it was brilliant. Okay, I can't actually give credit because I can't remember where I saw it, but I thought it was really good. And you know, if you didn't understand what I've just said about the significance levels, then just remember this, and you will get it. Right? So, say significance level of alpha, say 2.1% is low, i.e., lower than alpha, then reject HO. Okay. If it's higher, then you accept HO. Now, this is a question to try yourself. So have a go at that and just see how you do. You can pause and look through it. I'm not going to go over it. Thinking over it now, I think I should have probably actually gone over it, but I've already started recording and I think it's not that deep. Okay, now let's look at two-tailed test now. Now, it just means that we look at both ends of the curve. So last time we only looked at either the right end or the left end. This time we're going to look at both ends. Very little is different from one-tailed tests. Okay, significance level is different, just a very small amount. So say the significance level is 5%. Okay, and we have a curve like this, but we're considering both ends. Now, even if it's not symmetrical, this area is going to be 2.5%, and this other area is going to be 2.5%. Okay, and altogether their significance level is 5%. Okay, so for a two-tailed test, you always just half the significance level, and the area on the right would equal 2.5%, and the area on the left would equal 2.5%. Remember, everything within this blue region is the reject region. Okay, so if we're in this region here, or we're in this region here, then we reject the null hypothesis, because there was a high probability of it being low. Or if you prefer, if P is low, reject HO, or if the percentage is low, reject HO. And everything outside of this blue region, so all of this, that is the failed to reject region. In other words, it's the region in which we accept H naught. Okay, say if this significance level was 10%, we do the same thing here. This would be 5%, and then this would be 5%. Hopefully that makes sense. Okay, if the question says that P has changed, or sorry, if P has changed, right? If they specifically use the word changed, it will always be a two-tailed test. Okay, that's just the way to know. Just a little bit of extra information. It's true for any this here, which I'm just about to show you, is true for any binomial distribution, whether one or two-tailed. Okay, whether a one or two-tailed hypothesis test. So if you have x is distributed binomially, I've forgotten the b so many times. I think it's just because I've copy and pasted equations over. But n times p, so np is the mean. Okay, for example, we flip a non-biased coin 10 times. What's the average amount of what's the average amount of heads we will get? We will get heads? No, just we will get. I don't know why I put that there. Okay, I've remembered the b this time. It's non-biased, so 0.5%, sorry, 50%, which is 0.5. So the amount of times that we expect to get heads is 10 times 0.5, which is just 5 times. Okay, another example. Let's say we flip a biased coin 125 times. What's the average amount of heads we will get if heads get heads? Amount of heads we will get heads if the... I don't even know what I'm doing here. I can't lie. I just can't write or speak. If the probability of heads is 0.7, right? So there's 125 trials. The probability of getting heads is 0.7. So the average amount of heads we expect to get is 125 times 0.7, which is 87.5. Depending on the context, you can round this or not. I've just rounded here. Okay. Let's look at a two-tailed test question. Yeah. Okay. This is from an edXL paper. No? Okay, so a nursery has a set containing a large number of coloured beads, of which 14% are coloured red. Okay, so H0, what we're assuming to be true by default, is that the probability is 0.14. Right, you just do this from the get-go. Okay, Alia takes a random sample of 18 beads from the sack to make a bracelet. Okay, cool. After several, by the way, this is yeah, a nursery. Okay, yeah, good. Because I've just picked out specific parts of the question which we'll actually use, because this is other stuff that I'm not going to go over. After several children have used beads from the sack, the nursery teacher decides to test whether or not the proportion of red beads in the stack has changed. Notice the word changed, so it's going to be a two-tailed test. She takes a random sample of 75 beads and finds 4 red beads. Okay, now whenever you've got a sample and with it you have an amount, okay, of times you've gotten a success from that sample, that's going to be your distribution. You're going to use this sample as your distribution. I know it says this is a sample of 18 and then this is also a sample of 75. Ignore this 18 one here. This 18 one actually relates to part A of this question or part B. It's one of the two. So ignore that. I know it might look confusing, but you can just ignore this because it relates to a different part of the question because I've just cut out the bottom part. But you would say X is distributed with a sample size of 75. Okay, anyways, stating your hypotheses clearly, use a 5% significance level to carry out a suitable test for the teacher. Now, she's looking for the probability that it's changed. So, I've just underlined change there. We're saying the probability is not equal to 0.14. So it might be greater than 0.14 or it might be less. We're not too sure. We just know that it's not 0.14. Right? X is distributed binomially with a sample size of 75 and the probability of 0.14. Okay, this is assuming H0 is true. Like I said, remember, we're just assuming H0 to be true just to see how things play out and see what happens. Now, the significance level is 5%. Okay, and we have to actually define this test statistic. It's the number of reds, the red beads. Okay, that's what we're actually looking for. Okay, so we have the probability of X. Now we don't know how to check if it's greater than or less than, greater than or equal to or less than or equal to 4. Okay, we're not too sure. Let's think about this as logically as we can. What's the mean, right? What's the expected number of times of us getting red beads? Well, that'll be 75 multiplied by 0.14, which is just n multiplied by p. Okay, that is 10.5. Okay, we expect to get 10.5 red beads, but we've gotten 4, right? So, you know, this is much less than 10.5. So we're looking for the probability that it's actually less than 0.14. And so it's going to be less than or equal to 4 here. Okay, hopefully that made sense. You put that into your calculator. I'll actually do it again this time, just so you can see what it's like. Just in case you've forgotten. Let's look. So I'll do it from the start actually. Okay, so go into menu. Go to distribution if you have distribution. If you don't, press statistics. Okay. On your other calculator, if it doesn't look like this, it'll say list or one variable. Press one variable. If it looks like mine, press distribution and then press binomial. Now, on your calculator, it'll say binomial CD or binomial PD or BCD or BPD. We're looking for a cumulative distribution, so we're adding up 4 plus 3 plus 2 plus 1 because we're looking for the probability of it being 4 and 3 and 2 and 1, so or 3 or 2 or 1 or 0. Okay, it's a cumulative because we're adding up the probabilities, so we're going to click binomial CD. Okay, now n is going to be 75. Okay, so plug in n is 75. Okay, now ignore my lower here. We know that the upper is just going to be 4, right? The upper bound is 4. Hopefully that makes sense. And the probability is 0.14. That's already there, so we'll leave that. And let's click execute. So we get 0.015. Okay, hopefully that made sense. So this is 0.015. Okay, I'll just move stuff around a little bit. That's still the mean. Whatever, I've not changed anything, I've just moved it around. We have a significance level. Remember, we have 2 regions because it's a two-tailed test because we saw the word changed, and we can tell because this is not equal to sign. If it's a not equal to sign, it's always a two-tailed test. Okay, so we've got this region here and this region here. If the full regions both add up to 5%, right? So we can just half it to find 1. So this one here will be 2.5%, this full area, and then this one here will also be 2.5%, this full area. Okay. Oh, but actually, you can put in 2.5% there if you want, but like I said, because we're looking for less than or equal to, we're going from the left, right. So we're going from the left and then onwards 2.5%, okay, because it's less than or equal to. So that's 2.5%. Now, the probability that it was a coincidence is 1.5%. That's really low, okay? That's a really, really low percentage of it being a coincidence. Okay, that's this full area here. Now, if you look in relation to this full curve here, right, this probability of being a coincidence is really extremely low. Right, that's not even correct grammar, but you know, it's such a low probability. And because it's also less than the significance level, we can reject H naught. And this is our evidence, because this evidence is saying that it was a really low coincidence to get this. So we should say that, well, P should be lower, right? Because remember, our mean was 10.5, right? But we got 4 beads. That's a massive difference, right? That's 6.5 beads difference. Okay, so we're saying that P should be lower, i.e., which implies that the mean would also be lower. Remember, the mean depends on P because it's n times P. So if P was lower, we'd have a lower mean, which brings us closer to having an average of 4 beads. The average might not be 4, but you know, we want to be closer because the probability of this being a coincidence is really low. You know, this is more accurate than this. Okay. I've just said aloud what this is here. Another way to rephrase this part here is 4 or less significant, i.e., is it extremely unlikely that we get 4 or less since this was less than the mean? Okay. Or I could say we just got 4 reds, 4 or less reds. I'm just gonna say 4 just for simplicity. We just got 4 reds. Was that very unlikely? And it's getting even less reds, super unlikely. So just as unlikely. Or I could say, was this sample significant to suggest that the mean should actually be different? Or was this a significant result to say that, well, H naught is false? Okay, if that didn't make sense and you don't like that phrasing, then just think about it as this is the probability of this being a coincidence, which is extremely low. If it's less than our threshold, which is 2.5%, then we reject it. 2.5% is the maximum it's the maximum percentage of coincidence which will not which will barely shy away from, right? Hopefully that makes sense. Let's try another one. Past information shows that 25% of adults in a large population have a particular allergy. Okay, so we're saying that H naught is 25%, 0.25. Ryan believes that the proportion of the people that has the allergy differs from 25%. So he's saying it's changed from 25% to something else. If it differs, it means the same as changed. It's not equal to 0.25. Okay, there's a sample of 50 people. It actually tells us the null hypothesis here. The significance level is 5%, and Ryland finds that 10 of the adults in his sample have the allergy. Okay, so 50 adults, so sample size of 50, probability of 0.25. This is assuming H not to be true, and I've forgotten to put B here again. Okay, hopefully you know, you're one of those who know that I've just said that multiple times, so hopefully you know that what am I even waffling about? You know what I mean. You know what I'm on about. This is a B here, if you just imagine it. Okay, so this is assuming H not to be true. Our mean is going to be 12.5 because it's 50 times by 0.25. It's 50 over 4, which is 25 over 2, which is 12.5. Okay, because 10 is less than 12.5, that means we're looking for the probability that X is less than or equal to 10. So that's less than or equal to the number of successes from the sample. Okay, I'm not going to explain why this is. Again, I did it on the last question. Maybe just listen to that over again if that helps you. Okay, so probability of X is less than or equal to 10. We need to define the test statistic. So X is the number of people who have the allergy. Okay, so that's 0.26. Putting it into your calculator. Okay, remember, go to 4 decimal places. I've not, just because it's easier for me to write it like this. But yeah. Okay, cool. The curve looks something like this. It's actually probably skewed, but you know, this is just a rough sketch. This here is 26%. We have a significance level of 5%, right? So we've got this region here, and we've got this region here. This region is 5%. Sorry, no, it's not 5%. This region is 2.5%. Ignore that. That should say 2.5%, not 5%. That's a rookie mistake. That does, just imagine there's a 2 point in front of this. I don't know why I put in that. I must have just not been paying careful attention. But this is 2.5%. I've said it multiple times. Yeah. Okay, cool. 26%. So going from the left, because it's less than or equal to. So going from the left, 26%. That's this height here. Okay. 26% is greater than 2.5%, right? Which means that there's a 26% chance that this was a coincidence, right? That's higher than our threshold, right? We're accepting anything that's higher than 5% chance of probability. We're saying, well, you know what? That was just a coincidence. So anything that's higher than the 5% chance of it being a coincidence, we'll just say, well, that's just a fair coincidence. We can't do anything about that. Anything that's less, that has a coincidence probability of less than 5%, we're saying, well, that's really unlikely. That's a really low coincidence probability. So yeah, right. But here there's a 26% chance that this was a coincidence, right? So you know, we can't necessarily say that H0 is false. So we accept H0 because there is sufficient evidence to suggest that P does actually equal 0.25. Okay, hopefully that makes sense. That's from that paper there. This is another one. This is from, oh, I've actually not put this paper. Oh, I've forgotten where it's from. It's an AQA AS level paper. I have done it on my channel before. It's one of the it's the statistic paper, so it'll be paper 2, and they don't have many papers. They're not the legacy papers, by the way. So they don't have many papers. It won't take you too long to find this question if you do want to do it. I'm going to ask you to do it now. So yeah, please have a go at it and see how you do. And yeah, that's everything. Thank you very much for watching. I hope that helped you.